Quantum entanglement is a term coined by and researched by Schriener, although discovered by Einstein in 1935, to describe a specific phenomenon between particles at a nanoscopic level. It's a complicated connectivity that isn't yet fully understood, although the concept has many theories behind it. But first, what does quantum mean? This refers to quantum physics, aka quantum mechanics, which can most simply be described as a branch of physics dealing with interactions at the atomic level. Quantum physics differs from conventional physics, as at the atomic level, normal and reliable rules don't apply, and the processes can become immeasurable with the size of the particles. Quantum mechanics is heavily based on probability because of this. Well then, what's entanglement? Entanglement arises naturally when two particles are created at the same point and instant in space, and samples can be done of this in high-tech labs. The particles that are created together become so deeply linked that they seem to share the same existence, functioning in ways that weren't thought possible. Well then, what can they do when they're linked? As particles are created, whether it be in a lab or a natural occurrence, many alterations of the particle's quantum state occur, sometimes leading to the connection of two seemingly separate particles. The entangled particles will be synchronized in a specific way between the polarization, spin, momentum, and velocity. In other words, they're going to share a bond which allows the spin of one particle to oppose the other, so the spin of one particle determines the spin of the other. So if particle A spins up, particle B will spin down. Not only that, but this happens instantaneously. No matter the distance, they'll seem to communicate without any apparent need to travel across the distance. We can determine the spin of particle A by observing B, although ultimately we have no control over the spin of particle A. It gets interesting as the correlation seems to defy physical laws, as the particles are synchronized over any distance whatsoever. Whether they're in the same lab or 2 million light years apart, they will determine each other's properties. Again, the spatially separated particles will remain immediately synchronized with each other's alterations regardless of their fluctuation in space. It's not possible to determine which measurement came first, since the transfer is instantaneous, so the cause and effect create a paradox that has been troubling scientists. Einstein described this phenomenon as spooky action under distance, which is pretty accurate. This inseparable relationship has been referred to as the God effect and is regarded as one of the strangest scientific phenomena to ever be observed. Controversy. The laws in which quantum entanglement seem to break baffle physicists as they try to understand how the lack of measurable delay for communication was possible. After all, the fastest known thing in the universe is light, right? According to the theory of relativity, quantum particles wouldn't be able to have instant information transfer because it would be faster than the speed of light since they synchronize over any distance whatsoever. The speed of light is only 1,079,252,848.8 kilometers per second. That's a lot of kilometers. Without throwing years and years of physics research out the window, scientists try to explain what might cause this to happen. Perhaps the separation of particles is an illusion in how we view them, and this is why they share the same existence. This could potentially explain the violation of natural law. Another proposed idea is that the particles are communicating interdimensionally, or even that they contain hidden variables from the moment of separation and there's no actual transmit of determining data between them. These variables would be able to decide spin factor without having to send and receive the information. Overall, the lack of measurable delay is something that we can only theorize about without more advanced technology. How does this affect us, or to put it bluntly, why should we care about such a seemingly abstract concept like this? We're discovering more and more ways quantum behavior affects us and how we might be able to utilize this phenomenon in the future. For example, one study suggests that the DNA double helix would gain stability by entangling the electron clouds of two nucleotides. And if that isn't cool enough, studies show that migrating birds possibly utilize entanglement to increase sensitivity to Earth's magnetic field, allowing them to find their way easier. So yeah, that's all. It went downhill.
One kid in the audience would be like, yeah, it wasn't cool enough.